like you should apply. And if you are applying to events, so we had this. I forgot the name of the award. Texim got this award.
Yes. Texim award.
Daryl Chong event
Yes,
activity
yes,
award. Okay,
yes,
so
yes,
that has
yes.
three categories. So you should also apply to
Mm-hmm.
that as well.
Okay. Yeah. Like we'll just see like what we can do. But slowly we are progressing. Actually, it's a good from a. Okay. So anyway, thanks once again for accepting to give this talk. I believe we can now start actually. So yeah.
Tamoghna, thank you very much. This is Suposachi Mukhopadhyay, Vice Chair. So
Yeah,
thank you
hi.
very much for accepting the kind invitation. So let us start our event. So
Sure.
basically, our chair Kumarji will host the session. And Tamoghna, just for your information, one of my known candidate, Dr. Anjun Choudhury, recently joined a couple of months ago at the CSC department of IIT ISM Dhanbad. I will tell him about you. I
Okay,
think you may know him.
I once meet him.
Uh,
Uh, yeah. Anjan, yeah. He did PhD from ISI.
yes, Dada.
Okay, I met him. I met him once, only once. But I didn't have masters.
Mm.
Okay, great.
Thank you, Tamoghna. Looking forward to your excellent talk.
Okay, sure. Okay,
Okay.
so I think I am not seeing here that student match logo. I think the student match logo, that is there.
This one.
It's actually designed that time by me actually.
Okay, sir.
Oh,
Is this
great to know.
this
Great
one?
to know.
Yeah. Okay, so maybe I'll just share my slides and we can start.
Sir, before that, a little bit of
Okay.
introduction.
Yeah. Okay. Yeah.
Okay.
Please go on.
Okay. So, good evening, everyone. My name is Kumarjit Ray, Chair of CSSBC IEEE Kharagpur section. So, today, our speaker is Dr. Tamoghna. So, before introducing about him, so let us introduce about our SBC. So, in our Complex Society SBC, we used to conduct different types of technical talks, then some workshops. So, probably in the June month, we are going to plan some offline events also. So, uh, in this SBC, Mr. Sabyasachi Mukhopadhyay is the vice chair, and Rajdeep Ghosh is the secretary, and Angshita Gupta is the treasurer of our SBC. So let me introduce about our speaker. So in short, like Dr. Tamoghna Ojha is an assistant professor at the Department of Mathematics and Computing in IIT ISM Dhanbad, and he leads the computing for secure and intelligent networks, popularly known as cosine labs. Then he has also previously served beats SRM University, and received his master's and PhD from then he has also worked as an ERCIM, that is Align Bensosian postdoctoral research fellow in the year of 2021 at the Institute for Informatics and Telematics in National Research Council CNR Italy. Then he has also worked as a research consultant with the Department of Information University of Pisa for 3 months. Then he has received grants like exceeding over 1 crore INR from different institutions like government and non-government organizations. His research focuses on applying AI and ML techniques for IoT. Currently, he edge and non-terrestrial networks and wirelessly powered IoT 6G network and edge cloud continuum and digital twin also. Uh, he's the senior member of IEEE and the recipient of 2016 Richard E. Marwin Student Fellowship Scholarship, then winner of the Z Edition Challenge 2013 with Indian rupee 10 lakhs. Then he's the editorial board member of the Springer Nature Journal, that is scientific report, reviewer of multiple IEEE transactions. He regularly serves as the TPC member and organizing committee member of the reputed international conferences. He is also the core team member of IEEE India Council Technical Activities Group for this year 2024 and 25. So before starting the talk, there is a general instructions for all the participants. Like, please keep yourself muted during the talk, and please wait till the end of the talk to ask any kind of questions. There will be a extra Q&A session at the end of the session. Then an attendance sheet will be distributed. You can please note your attendance over there. And also, if you have any queries in the middle, you can write in the chat box. We'll include in the Q&A session. And also, we'll be taking a group screenshot of the event at the end of the talk. Then you can please, if possible, you can turn on your camera. We'll take some screenshots. So thank you, Dr. Tamoghna Ojha. So, like, you can start. And thank you on behalf of whole CSSBC team.
Thank you for the nice introduction, Kumarji.
Thanks.
And I'll just present now. So maybe I'll just switch off my video for saving bandwidth. Are you able to see the slides?
Yes, sir.
Okay. Okay. So thanks again, all of you at IEEE SBC and IEEE Kharagpur section. So today I'll be talking about the resource management aspects of future IoT networks. And so this talk, before going to this talk, it will be like, so mostly I'll be talking about a lot of different technologies. So IoT is, like, as you all know, might already have worked in some of the different research challenges in IoT. So it's quite vast domain, and to solve the problems, so there are newer problems coming up, and also with the advent of newer technologies, so it becomes that some of the problems, the solutions for some of the problems are becoming, to solve in newer approaches, technologies in other domains also, which also affects, like in development in the electronic side, uh, like VLSI side, they also affects how we design our algorithms. Quite a vast domain and quite a lot of challenges, and as a result, uh, like a very tasty, we try to solve these problems with with a very high. So, Kumarji already, told a lot of things about me, so maybe I'll not just discuss, but I'll just, try to highlight here that, talking at an event organized by a branch or the student branch chapter is a very emotional moment for me. And it's like, because it's first of all thing, it's like my alma mater. And second thing is that it's the student branch I was associated with kind of like 3-4 years, maybe. Started with being a volunteer, and then I became the student activity committee member. Then I became the executive, like chair, and UPP liaison. Then we organized an international conference. So in between, so this was like a lot of working with a lot of other colleagues, other students, other faculty members. So this was a very enjoyable moment that I really enjoyed at the time. So yeah, so moving forward. So in this talk, I'll be mostly talking about three different aspects. So, yeah. So I'll talk about three different aspects. So mainly I'll talk about, I'll start with some basics, backgrounds and all. Then I'll go to the communication aspects, computing aspects, and the energy aspect. So these three, I consider these three like, whenever I look at the problems philosophically, so I see that these three philosophical dimensions are there. Obviously, it can be argued that there are more philosophical dimensions, but to my research, these three dimensions are core part of it. Most of the time, these are like interlinked and interdependent also. And so overall, as a whole, my talk will be touching a lot of newer technologies, and mostly going to a not to depth, but mostly going through breadth of the technologies. And some of the works I have, but I didn't include that because those are works currently going on and published and all. So I choose to just keep it and keep the thing a little bit simple and broad for the whole audience. So let's start with the promise of Internet of Everything. So it, like, there are a lot of different promises. So you can see, these are like kind of a comical view of the whole research that we do. This is like a, inside a home scenario. This is like a outside, road kind of scenario, and this is like totally a funny scenario. So this touches. So the main point here is that we have different technologies, different types of devices, a lot of heterogeneity, and the spectrum of communication is very quite high. Narrow down the challenges. So we start with a hierarchical approach, like we can see here in this pyramid picture. So here in the bottom you can see that, okay, so IoT connectivity actually is provided by different sensors, IoT devices that can be like small devices like smart tags. It can be little bit big, a little bit size wise, or maybe like smart cameras and all. And so these are the ones that are like providing us the connectivity and working like a pervasive kind of scenario, pervasive and ubiquitous kind of scenario. And uh, so this will generate very high volume of data. And everything goes, most of the time this all this data are processed through a cloud server, centralized systems, cloud and data centers. And in between we have uh, some things which are providing connectivity between, which are like a bridging gap between these two layers. So those are the edge layers or edge gateways. So in principle, what we get here in the bottom layer, we get connectivity and networking, and in the top layer we get intensive computing. In middle we have delay-aware computing, and the data collected by the bottom layer is actually processed through, so we gather more data and we have knowledge. Then we have more knowledge and we have wisdom. So it's like, age level, maybe we'll have localized knowledge, or maybe confined to small geographical locations. But in the centralized level, in the cloud level, we have a wisdom that covers a lot of different geographical locations, a lot of different types of data types of applications and all. So when we see the use of AI, so they are in cloud, it's progressing in edge layers. Now, there should be another arrow, that now use of AI is also, in the pervasive layers, like in all three layers. Now we have the presence of AI. So if we see, so these are communication, different like applications and all. So I will not discuss about it. So if we see that the changing, network technology, like the traditional mobile technology, so we are moving from fifth generation to the sixth generation, and with a high promise that we will be having the with IMT 2030, you might have known that 6G will be, arriving by 2019 or 2030 maybe. But that is like they will just arriving, so it will not be that mature. And there are a lot of works are going on in different aspects of it. But to be have an overview, why we need 6G again if we have this 5G, everything is running fine. So with, like, I would like to highlight this in only one sentence. So with newer applications and all being developed, so there are newer demands from the application side, newer challenges being posed over the existing communication network. With improvement in technologies in different aspects, so we have potential to solve different problems. We have potential to deliver a better scenarios for like better like service for all these different applications, different users. So on to have summarizing in a few points, that in 6G we'll have AI in every layer. We'll have massive energy efficiency, and sensing, communication, computing, all this will be integrated, and it should be highly reliable with providing low latency. So some of the things, uh, so I'll discuss some of the things we try to modify. Are actually, some things are 5G plus plus, and some of the things are actually totally newly incorporated. Okay. So we'll see that in the upcoming slides. So as a whole, if we see from any general IoT applications. So what is the typical demand and what demand they can pose in the future. So one first thing is we need to have it meaningful. Like if whatever data we are collecting, it should be meaningful data. No, we should be meaningfully collect the data. We should not be unnecessarily collecting it. Uh, Sensors, like it should be available as per our need. It might not be available 24/7, but it should be. So maybe a part of intelligence also required here. It should be available whenever we require it. So whenever that is the question. Right? So whenever, when is the need? So that we need to estimate, and accordingly we need to activate all these things, all these devices. So it should be scalable. It is required. So we need to work the whole application maybe very high uh, geographically distributed part, and that can be like even properly. So it should be properly scalable, and it should be reliable. Like it should be like whenever I need, it should give me a proper value. I should be trusting the system properly. So here the aspect of security, aspect of attacks and all, as well as the aspect of fault, all these things comes up. Suitability. So it should be, some suitability is like, no, it should be, it's like a design choice kind of thing. So we need to be deploying proper sensors and all. We need to be deploying the sensors where it is actually needed, and we need to properly plan the architecture. It should be suitable to meet our demands. And obviously, all these are interoperable. So interoperability is a big issue here. Now, with with the computing models we have. So we have right now we talk about the so it's like I say it like this, that it's the rise of edge devices. So edge devices are getting powerful, and they are like rising in their capabilities. So that are that gives us faster data processing with more privacy, with reduced latency. So all this, so our you might know that whatever models we build, whatever AI we build, we if we don't have good data, if we don't have proper data, the models are not that good. So with this, the data sovereignty and the issues of privacy being increasing day by day. So the edge computing is a proper solution that can meet our demands, maybe single-handedly, or maybe I mean not single-handedly, maybe like having a more chunk of the processing should be taken in the edge layer compared to cloud, or maybe in a synchronous way, like the cloud edge IoT continuum kind of scenario. So moving forward, and whenever we try to design these solutions, what we try to do is we try to respect our home, that is the earth. We try to follow some of the guidelines that are being uh, provided by the United Nations as a good guidelines, that should sustainable development goals, because we are exploiting the resources available in our surrounding, and that actually hampering the earth, right? So climate change and all, you might be knowing, and not just climate change, it's also hampering different types of people, different communities, different areas. So I have listed here some of the goals that I feel that close to the sort of problems that we work on, and we should always keep these things in mind while designing some of the solutions. Like SDG 9 is about industry innovation and infrastructure. So these directly related to applications of IoT and edge computing as a whole. Affordable and clean energy. So this is like so with the increase in compute needs, so the demand in energy also increasing maybe rapidly. More the computing need, the energy demands are actually increasing quite a multiple times of that change. So accordingly, we need to have affordable and clean energy to support the computing demands, and sustainable cities and communities. So our goals should be to make the things sustainable, more sustainable, and for cities or for any like urban or whatever type of, and as well as for the communities. And there are very so these are some of the uh, sustainable development goals that are very close to the technology. And So then we have some broader goals also, that is reducing, like zero hunger and good healthcare. So SDG 2 and 3 talks about those. So in principle, we always try to uh, keep this in mind while designing our solutions. So with advent of newer generations of computing and newer generation of communication, so we have some of the, these are some of the enabling technologies that we see, or that we will be seeing more in the upcoming very near future. So we have terahertz communication. We have terahertz communication to support, more bandwidth, more better communication aspects. We have augmented and virtual reality to support different types of applications, maybe learning, maybe healthcare. Quantum communications, to leverage the benefits of quantum uh, entanglements and quantum communications. We can apply those things to, compared to traditional approaches of computing. We can use those properties to maybe better design the system, to make the system optimal. To secure the system, we use blockchain. So there are quite a few development already in blockchain. Mobile edge computing is obviously there for the last couple of years. Unmanned aerial vehicles, so the presence of unmanned aerial vehicles are unmatched, uh, be it in healthcare, be it in surveillance, be it in war scenarios. Artificial intelligence as a whole to be present in everywhere. We have other things like selfie communication, optical wireless, massive MIMO, as well as intelligent reflecting surfaces. So these are some of the technologies that will, change the way we use, our surroundings. So first, let's focus on the communication aspects. So if we see the evolution from 1G to this 5G and coming beyond 5G, 6G era, so you see that 1G was basically a basic one, like a nascent version of the technology, network technology we had. It was specifically for voice calling. In 2G, the feature of SMS came up, and 3G was where internet was introduced. So in between, we had, like, we can say that, okay, it was 2.5G, like GPRS or Edge, EDG, where the internet was actually there. But it was 3G where it was like a meaningful internet, just good speed and all. And then in 4G, we had a lot of internet applications, and it was massively focused on high speed, like increasing the speed of communications. Now in 5G, what happened? So 5G, the speed and all were increased with, increased reliability, increased energy efficiency, and so massive broadband, like EMDB and all, and introduced introduction of the IoT in the 5G sector. Now in 6G, so 6G, there will be new disruptive technologies like integrated sensing and communication. There will be newer spectrums. There will be, better energy efficiency, better latency, and use of AI in a better world. So if you see that the conferences in our domain that actually focus now on, these kind of themes, like, towards a fully digital and connected world. So our goal is to, like, connect the unconnected, tap in the like uncovered areas, tap in the uncovered communities. So all these are goals of the 6G, upcoming 6G communication. So if you see here, so this. So if you see here that, so we have compared here that, so this is like a typical comparison. It's not like, so these values might, vary little bit. Some of the things are like a kind of best case scenario. So 4G, 5G, and 6G, we will be, increasing, expecting the increased data rates and lower latency, as well as so higher mobility support. So integration of the satellite is a totally new thing here. It was not there. So these all are like, we are trying to improve from the previous technology, and this is like a totally new thing, the integration of satellite. So this I'll be talking in future slides. And use of AI. So like currently it is like partially, or like, it is gradually being increased. So in 6G, it is expected to be, like lot of use of AI. autonomous vehicles, more use of autonomous vehicle, extended reality, haptic communication, and so similar types like kind of projections and all, like we see in the Star Wars movies. So this kind of communications, and yeah, so mostly these are the important points. Yeah, so we have, the ITU is talking about different use of newer spectrums to provide newer newer advantage, newer connectivity in different areas. So mostly they are trying to use the high spectrum, like say uh, starting from the 4 gigahertz type band to 6 gigahertz. And in India, we are specifically, I think recently there was also news that this some part of the 6 gigahertz band will be open for improved Wi-Fi access, specifically for air gear type of applications or different type of other applications which uses this thing-to-thing communication kind of scenarios. So there are mmWave bands that are already, some of the things are already in use. So, and some of the higher bands like terahertz and all will be included in the upcoming 6G communication. So if we see logically, so 1G to 4G was like, people to people, and in 5G it became like people to thing, and in 6G it became like totally thing to thing. So where one of the thing can be people. So moving forward, uh, so if we try to summarize here the goals of 6G, so we see, there are three different uh, dimensions. So level 1, level 2, and level 3. These three are different dimensions. So first thing is to provide, connectivity, connecting everything. Second thing is to have a connected intelligence. So it's like just providing the connecting, and this is like providing not just connectivity as well as intelligence. And level 3 goal is that uh, to realize the actual values from from these connected systems, and to have massive reliability and all. So if we see from the 5G landscape, so this we already have ultra reliable low latency communication, massive machine type communication, and enhanced mobile broadband, right? So we are trying to improve that. So some of the new use cases, those are like will not be, these three will not be sufficient to meet those use cases. So we try to have improved one, right? Hyper reliable low latency communication. So this kind of scenario. So then we have integration of, sensing, localization, communication as well as computing in the whole thing to have a connected intelligence kind of scenario, so that we can, leverage more meaning from whatever information we get. And then we have, like more collaboration in the 6G, and more collaboration as well as more intelligence. Like the system should be, our demand is that it should be totally like zero touch kind of scenarios. Like, there is no like very less human involvement. And so let's see what are the, sub areas. So dimension was connecting everything. So we have, TBPS level data rate. Spectral efficiency should be, we should improve the spectral efficiency from whatever spectrum we are using, from spectrum, and we try to find more efficient communication from that. So more trust and privacy in each layer, like in the from the physical layer to application layer, there should be involvement of security and privacy issues. And yeah, obviously. So second thing was about connected intelligence. So here we need, what we are trying to do is, so first thing is that we focus on the spatio-temporal, environment. So let's, let's just see the first one, then we'll be. So second thing is understanding the specific, user equipment specific resource condition and spatio-temporal status of the devices that are surrounding us. Then we'll have, more a better, decision, a better intelligence about what is the condition of the resources, what is the condition of the resources if I move, or what will be the conditions in the future. So both in the space and the time domain. So that we get from, like both of these two sub points of this dimension 2. Understand the constraint that will be there in future time or in different space. And to improve everything, what we can do? So to provide a spatiotemporal intelligence, resource utilization, what we can do? We can have a collaboration between the vertical layers also, right? That we see in the pyramid picture. The device like cloud edge IoT continuum. So this cloud edge IoT continuum focuses, like most of my research interests are, some are also here and here. So in dimension 3, what we want? We want more value realization from this connected system, right? So what we want here? We want the system to be scalable in different conditions, different time, different workload. Expected workload also, it should be scalable and it should work fine. It should be very efficient to manage all these resources. It should utilize the resources more while minimizing the energy. So this is one of the first and foremost point challenge that we face while designing our algorithms, right? To we always get more energy consumption, but we have to design something which balances between these two, which keeps like a trade-off between these two, and the system should be agile for so that we manage the system by lightly moving, doing a fast orchestration, like the orchestra. There are they synchronize in a thing, and here according to network change, according to demand change, we should also be a fast changing scenario. Like we should also be able to change the whole resource allocation and all this scenario in a very fast way. Now moving to computing aspects. So edge computing we already discussed, right? So this has been this progress from the content delivery networks to peer-to-peer networks, and then we have micro data centers. Then we have more power to the edge. Now this has progressed also thanks due to like VLSI technologies, and also in the power sector like electrical side, so that improves the onboard like single board computers that we mostly use for the edge devices. So both in the VLSI as well as in the improvement in the battery technologies have made it possible to have onboard computing or on edge computing in on-premise computing kind of scenarios. So we always see that computing is good and all, but we like it's okay. It will provide with cloud. It will be like a longer delay. With edge computing, it will be shorter. Obviously, those are very meaningful. But what is the challenge to support or challenge to provide this kind of services? So let's focus few of them. So we have partitioning and offloading of tasks. So when we have edge devices, they have so the issue of resource management become more critical here. So they have less resources, less computing power, less battery, less onboard memory, maybe communication limited. And so with this, we cautious with our design, save all these precious resources. And so here it becomes the issue like how to manage the resources, be it computing, communication, or energy. So here, so a lot of time there will be no offloading between the edge node from edge to cloud, uh, from like maybe on-device computing also. So how to manage the decisions in all those cases? So there are already a lot of works are being done in mobile edge computing scenarios, but with use of newer technologies like say more presence of drones, more presence of satellite components. So these again become a focal point of a lot of newer researchers. So then we have to have unpromising quality of service and experience. So this is the main goal, right? Whatever we are doing, whatever technological changes we are making, these all are for providing a better service. Now, to serve the to serve the users better. So be it in the QoS point of view or be it in the QoE point of view. So these are the goals that we do our work for. And so some of the other aspects like finding out edge node, placing services in the edge node, like where we should place it, which service, because there may be different class of services who need different levels of resources, different commitment from resource side, different privacy. Uh, Accordingly, discovering edge node and placing service also very challenging work. So also to provide all this, securely is also very challenging thing. So with as you can see that cyber security is becoming, and with a lot of other scenarios, geopolitical scenarios as well. So now edge nodes. So here I'll just try to specifically highlight a point that what are edge nodes can be. Now this is a this quite there is no standard definitions of what can be edge. So it depends, varies from application to application, varies from use case to use case. So and there are different other names also, fog node, cloudlet. So it didn't become more popular like cloudlet name, but fog and edge become more popular. So maybe for say telecom type of application like telecom infrastructure application. So edge node can be a cell tower. For intelligent transport systems. So it can be the autonomous vehicle or the roadside units in say manufacturing industry. It can be a smart equipment like a machine can be a edge node, or maybe there can be a separate edge node that can monitor a whole room or a whole floor. This kind of scenario. For surveillance, the camera or the CCTV may be working as a edge node. So we use different types of SBCs, single board computers for serving our purpose. So they may be powerful like say Jetson devices like Orin and all, Orin or Jetson or Nano, or maybe very low power like Arduinos and all. But if you might already know that there are Arduinos are also nowadays capable of running machine learning models like tiny models and all. So it's also so these are also growing in more importance. And we also have Raspberry Pi, which is like the favorite of everyone. So yeah, so there are billions of devices supported by millions of edge nodes, and maybe supported by thousands of nodes in the cloud data center. And we are seeing more use of AI on this case. So edge AI, when we say that AI should be applicable to edge devices, what can be the different types of model deployment, types of architectural point of view? So one can be like, so the device itself run the machine learning model, right? So on device computation. Second thing can be like a secure two-party communication where the device communicates with some other party, like some maybe edge server or maybe uh, cloud. So where they send data, the data is being processed by a model running in that remote device, and it gets back the inference. There can be another scenario where the model is partitioned. This is also very interesting. That how to partition the model, how to resource our model partitioning, or demand and resource jointly demand and resource our partitioning. So this is a very promising area of research even nowadays. So here what happens that the model is actually partitioned in different some of the layers may be running on the edge device, some of the layers, maybe middle layers, are running uh, in a hierarchically middle edge device, and other layers are running in the cloud side. So here also this cloud edge continuum things become more relevant here. Other models can be like we have compute offloading, like partial uploading of data, and so local model and and a global model both are running, and jointly it will be, the inference will be processed jointly. So some part of the thing is running locally, some part is running uh, like in the remote server, maybe edge, or maybe in the remote cloud. Another model can be, so this is the future here. Another model can be, so here orchestration and relevant related issues are becoming relevant here. So we separate the model among different like horizontal level, right? So these are different edge devices sharing the execution of the model. So so here, this is a very promising area, and this is also a very challenging area for research. So how to distribute the computation, how to partition the model in these different horizontal layers, and not just horizontal. Maybe with these horizontal layers, there can be vertical layers can also be involved with this. Okay. So let's move forward. So with this, we have a very interesting case scenario that is called integrated terrestrial and non-terrestrial networks. So if you see this picture, so we last couple of years we have seen that growing use of drones, and so typically we have this drone like UAV IoT networks. So there can be different scenarios like UAVs can be working as users, and they want compute uploading support from the base station, or UAVs are providing service to IoT devices, or it's like UAVs are simple like like a relay, or a data mule or something. So these were the typical use cases. Now this has evolved. So with the presence of satellites like LEO, MEO, and as well as GEO. So or the involvement of different high altitude aerial platforms like in short called HAPS, like this balloons and all. So so compute and communication has grown vertically as well. So not just horizontally. So now we have so as a whole, this is called as integrated terrestrial and non-terrestrial network. So these are the non-terrestrial part, like drones, HAPS, satellite components. So these are the non-terrestrial part, and these are the terrestrial part, right? So with this, we have a total integrated solution. Now it has other names also, like some people call it SAGIN, like satellite aerial ground integrated network. So I view this as a aerial edge computing paradigm, where like simple things like drone as a service, aerial computing as a service. These are some of the things people are working on. These are some of the things being very popular, and with now like people are seeing this as a whole as a integrated terrestrial and non-terrestrial network, and that newer challenges of like say mobility of these aerial components, uh, asymmetric connectivity, unreliable connectivity, all these aspects people are looking at. So with this, we already have like, so I have just pointed out some of the newer challenges here. So the aspect of delay, aspect of energy management, these are already there. I mean, these are being there, but with involvement of non-terrestrial components, so we have more dynamic topology. And so whatever topological challenges we have it here in a massive scale as well as with mobility. So the promise of 6G is here that it should be supporting, we should include this, like compute can be, HAPS can be a edge compute service provider, satellite can be edge compute service provider. So there are already, like there are already some of the Indian startups who are working on this kind of scenarios, where they try to use satellite for edge computing. Like I am also working on some of this direction where we are trying to have long range communication between satellites as well as with the ground device, or involving with the aerial component as well. So they have potential applications. A lot of applications can be there. Maybe mostly people see it disaster recovery kind of scenario where people see these are to be remotely deployed. There can be infrastructure monitoring, and also there are surveillance as well. But the use case for urban areas are also increasing, which you can see in this satellites can also provide a means of compute support, where in urban areas typically we have a lot of compute and communication demand. So this can be alternate service providers here. So moving forward, uh, so typically what we have in this, we have this space, aerial and ground layers. So edge server, where to deploy this edge server? Now again, this is a question which can be application specific, which can be both application specific as well as so while designing the solution, we should keep in mind the application requirement as a whole, uh, also with the other requirements that can arise in that challenge. So like it can be deployed maybe in the base station in the aerial components, or maybe in some of the ground layer components as well. But the cloud is obviously it will be a remote one. That can also be mostly be in a remote ground layer or as well as in a space layer. So computation can happen in every layer, like collaborating. The layers should also have collaboration among these. So typically we see these challenges are these battery challenges, mobility challenges, satellite related challenges, like the satellite can the predicting the path of satellite, predicting their FOV, like field of view and all, and accordingly try to activate the IoT nodes, try to activate the aerial components. That is also another challenge people look at. Security aspects, like so there are more compute elements, so there are more chances of attacks. There are more challenges from the security point of view. So, okay, so it's like an extension of the previous discussion. So here we can also have drones, swarms of drones, like they may be deployed on demand, like ad hoc fashion, or they may be as a part of like the apps may be a part of the whole communication infrastructure, and can be like a opportunistic service provider, or a like sometimes it may be available, sometimes it might not be available. So the uh, planning of computation, offloading, planning of managing resources again becomes challenging with all these uncertainties. So yeah, so now from the offloading point of view, we have typically have two types of offloading. One is binary, another is like partial. Now binary is like okay, like either we do it here in this device or we do it in the other device. But partial is like okay, we do model partition, or we do like we do compute level wise partition based on, say, like in the example use case here we have these three users, they have different energy levels, and accordingly the partition decision has to be done. So they might have different amount of resource also, like heterogeneous amount of resource also. So accordingly we have to take decisions about how we which person should do, like which device should do how much computing, or how much uploading should be done. Okay. And in the vertical layer there can be like a decision of partial as well as binary uploading also. So this side also can be like okay, we'll do everything here or we'll do everything here, or it may be like okay, we'll do 60% here, 40% here. Now that can depend also on the service demands, service level agreements, quality of service that we focus on. Some of the AI related models, like we have deep reinforcement learning as a whole, has a lot of relevance to this type of computing model, mostly because of its reinforcing capabilities, because of its self-learning capabilities, because these drones, these aerial devices, they can learn on their own, and they can be better in decision making. So deep reinforcement learning uh, like deep Q networks. You will see deep Q networks. You will see different this policy variants, policies regarding the reinforcement learning are becoming more and more usable in different different other researchers' work. Obviously, as the computing goes distributed, we have more importance on federated learning models. Uh, there are also models on federated reinforcement versions. There are tiny reinforcement versions. There are tiny federated versions, as well as there are tiny federated reinforcement versions. There are as well there are transfer learning versions. So, with due to time limitations, we are not going to discuss more on this. So, what other promise we have is use of IRS, intelligent reflecting surfaces, and digital twins with it. And it can be so not just aerial wise progression. We can also go towards the underwater layer as well. So this is the future of in future people are trying to plan for this kind of scenarios. Now, for a digital twin, some of you might already know that. So we try to have a replica of a physical component. Now, it's not replica which can do which can have real-time connectivity both ways, which can do which can predict the future, which can be interactive, which can be like resilient, like okay, it can understand that there can be a fault and it can make certain changes in the whole scenario. Now, challenges are that how do we construct this digital twin? How do we so to have exact replica, how much data we should collect, where we do the optimization, where we do the quality checks, where we do the security algorithm plus security checkpoints, where we do the edge computing kind of thing, where how to allocate resources for this. So these are some of the questions relevant to digital twins, and so that has a lot of applications in say as a whole communication infrastructure providing, or in different other areas like smart buildings, smart manufacturing systems, these kind of scenarios also. So there are three different class of digital twins where so mostly where we have both way communication as well as it should be an evolving replica. Previously there was a technology which also now in use that is called sensor cloud. So digital twin is can be considered as an intelligent version of better optimized version of sensor clouds, where it not just collect data, not just take decision. It understands. It has a wisdom to understand the behavior. So yeah, digital twin based edge network can be there. For there can be aspect of efficiency, latency, security, as well as fault tolerance to be looked at in this kind of scenarios. There can be a lot of other applications also, as you can see here. Now, okay, let's move to the energy aspect part. I think time is no time. Okay, so I'll just try to wrap up in maybe 5 to 10 minutes. Now, energy aspect, I think this is the main one, right? So if we don't have the energy to power the devices, we are basically we don't have anything. So a lot of devices, a lot of type of highly available devices, different demands they are serving, different scale of operation they are managing, but are they really empowered? So this is the basic question we ask when we discuss this question of energy requirement. So we see that connectivity is wireless now, right? So we have moved from the wired connection to the wireless connection in our surroundings. But energy is still, in cycles. Energy is still bound to the wired connectivity. So we are still dependent on the onboard capabilities. So here we'll discuss one promising technology like the wireless power transfer technology, which can be a promising solution to build wirelessly powered IoT systems. So what we do here, we try to like in the last few years, people are trying to do harvesting the energy, like maybe last more couple of years. So they are trying to reducing the need of batteries, trying to reduce the cost, trying to make a better sustainable. But this whole energy, harvesting energy from the whole systems is only a part of the challenge. It is solving only a part of the challenge, because these different type of energy sources, they have different properties. Like say solar, only available in the during sunlight, and it can vary geographically. So maybe like a tropical country have more, but the like say Europe and all these areas, maybe it can be less. Thermal is also depending on activities, ambient. Sorry, I'll come to this later. Wind is also one which is not available every time. So they have different power, uh, like efficiency, power density. So we have another source which is always present, which is kind of surrounding us. So that is the RF. So if we harvest the RF energy, that can be another promising case. So moving from this, harvesting energy from other sources, we are moving towards harvesting energy from RF sources, and trying to orchestrate. So here I will discuss some of the uh, wireless power charging technologies that I have worked on. So I'll quickly go through those. Now, the most basic challenge in these technologies are that, so it is still, there are, it is like practically they need to have a very close proximity to have wireless charging with most of our devices, like especially the small devices like mobiles and all. So they need to have a very, few, like say millimeters and centimeters gap to have a wireless charging. But there are some of the technologies which, like using say drones, high-end drones, those are like it can support up to few meters. I mean, not so much, maybe like couple of meters. So this is the overall scenario in the wireless charging cases, and there are a lot of companies they are working on, and there is also a standard which is called QI. So this standard is followed in the mobile phones that some of you might have. These high-end phones like designed by iPhone, Huawei, and all, or maybe Samsung. Must this electrical side of it is dependent on three most promising technologies. One is inductive coupling, which is mostly used in the smartphones. Magnetic resonance, which is also used in some of the industrial system, and radio frequency one. Okay, now inductive is the promise, like most used between magnetic and induction, and RF1 is growing in importance with like different type of devices. But also with RF1, even if RF is surrounding us, it can be unpredictable, because of transmitting the RF like signal, transmitter equipment is required, and if that is unreliable, that is not available, so it can be a problem for harvesting energy from that source. So that is also required to be managed in an intelligent way. So I previously worked on one of the subversions of this WPT, wireless power transfer technology, that is called the peer-to-peer version. So where we have typically this, like that mobile, like charging pad, or the mobile can charge this device. Peer, like from mobile to mobile charge, or mobile to other device charge. So as a whole, this creates a scenario called crowd charging, and so we'll see what are the challenges of those crowd charging models. So what we try to do in a crowd charging scenario is that we try to reach a energy balance level, where now, as you know that, okay, this wireless energy, so there is a loss associated with it, and it's quite high compared to traditional wired systems that we have, wired charging systems. So typically there are around 20% of the energy get lost when we exchange energy. So if we we receive only 80% of the transmitted energy, and there are challenges like if we transmit more energy, so the energy loss will be more. So we'll be basically losing some of the energy if we meaninglessly transmit, right? So Similarly, we have uncertainty in the energy transfer. So we need to have two devices coming to close proximity to transmit the to have energy exchange. Okay? So that can be uncertain depending on mobility. To come to close proximity, people willing to spend time to charging and to reach energy balance level. We actually will not be able to reach that theoretical level. So there will be uh, always a gap. So that we try to capture in the variation distance, and we try to minimize this distance. So typical challenges are uh, that okay, if we meaninglessly transmit all the time with all other users, that is not going to help us. If we don't consider the mobility, we try to estimate the mobility, then it will be better for us. If we do fully distributed one, that might not be a good solution, that might reach mostly local minimums. So a better solution can be like a central, like a federated one, like a central as well as distributed balanced approach. So I'll discuss here four different works that we did. I'll just put a highlight of it because understanding this will each of these will require at least 20 minutes. So firstly, we try to do a mobility prediction and then select the peers intelligently. So we try to predict the mobility from their previous history, and then we intelligently select which device should transmit which one. Now here we have a consideration. We have an assumption that these devices. Let me go back to the previous one. So we mathematically model the scenario like we have n number of locations, and in each location there are different number of charge provider as well as charge receivers, and we are assuming that whatever pair of peers will select, whatever the pairs we select, they will be coming to a close proximity to exchange energy. Like they are like totally they will follow the instructions of the algorithm. There is uh, no other disturbance in that case. So we do a peer selection based on understanding the mobility patterns. And so this work was one of the best papers in ISCC. And then we extended this work to consider the social information, like where, because some of these devices, they are mobile devices, they are carried by human. And human mobility will obviously affect the uncertainties for energy transfer, right? Now, what affects the human mobility? So we have social information which can affect the human mobility. So we try to we try to explore the possibility of considering mobility as well as social information to better model the uh, PR selection problem. So we considered social context, right? People can have different preference to visit different places, and people have different number of social friends in different places. So these two can hamper their mobility, like how much time they will stay in that place. Accordingly, uh, accordingly their duration and their next location can be changed. So accordingly, it can also affect the peer selection problem. So we dissolve this whole thing in three different aspects. One is this energy domain that we already had, and the mobility part is now dissolved in two different cases. One is location attachment, and second thing we call it as a social attachment. So location attachment is the context, social attachment is the relations between different friends. So here we try to create one parameter called the probability of selection, considering the probability of selection between any two devices like UI and UZ, where we consider these three domains like energy, location attachment, and the social attachment. Okay, so this was an extension of the previous one. So as a whole, if you see here, what we how we try to evaluate the whole thing is we try to consider different locations and different number of nodes with random energy values of like from 0 to 1 to 100, it's like 1 to 100, and we try to see this how much energy we are losing how much good in reaching the energy balance, and how quickly we are reaching those, with how many number of meetings and how many number of iterations. So these are the thing we try to uh, evaluate our, and yeah. So these two were like the network related aspects, right? So one is like human mobility, like the architectural aspect. Another is so these two are, we call it as network dynamics. In the next other two problems, we considered device dynamics. So the aspect of battery aging. Now battery aging cannot be stopped. Only we can do this. Say only we can reduce or prolong the battery aging case. So here we see the possibility of using wireless power transfer technology to slow down battery aging. And okay, I'll not go. We are already late. And in another work, we have we have tried to explore the heterogeneity aspects of the different devices. So we have all these mobiles with, say, some with 5,000 mAh battery, some with a better wireless charger, or some with less wireless charger. So we consider these two heterogeneities: heterogeneity in the charger, heterogeneity in the battery capacity. So we try to model a heterogeneity aware peer selection method. We try to have a model which is heterogeneity aware, and then we select the pairs intelligently, and then we do the actual energy transfer. So okay, I'll not go in the details of it. Yeah. So consider network dynamics and device dynamics, and maybe some of the future works that currently I'm also working on. One of this, to better make it better in one of these works, where we try to model more realistic energy consumption patterns and more realistic usage pattern to take better peer selection. So yeah, AI/ML, how it can be used in this area. So it can be used for optimizing energy consumption. It can be used for optimizing the charging. It can be used for power routing. Like one, if we charge one device based on understanding its mobility, can it charge multiple devices depending the route it is following? It can also be used for AI-based fault detection and maintenance in the energy systems, so that we have a better crowd charging platform. And obviously, there are involvement of UAV as a charge provider actually creates a better, like a towards wirelessly powered IoT. We can have wirelessly powered IoT nodes wirelessly powered by UAVs, while they also provide computing and communication support. So computing, communication, and energy as a whole in this whole scenario. So yeah, some of other aspects like people have worked on throughput maximization and the resource allocation problem as a whole, like how to allocate the power, how to allocate time for communication, how to allocate time for energy transfer, how to do the compute management along with the energy demand management, how to do both throughput, when the UAV is working as a data mule or something, or compute provider. So how to do throughput maximization as well as uploading as well as energy. So these are the complex type of problems. People are still working in different areas, and with involvement of tiny AI models, deep reinforcement learning models, there are a lot of scopes for work here also. So yeah, so these are some of the references that I have not mentioned previously, and some of the references are already there in the footnotes of each page. So yeah, so thank you. So now let me have questions from you.
So if anyone having any question, they can ask directly, or they can type in the chat box also.
So maybe there are a lot of components I just tried to cover in this whole short duration.
Probably there is no question in the chat box.
Okay.
So we have got few questions while people have applied like registered for this session.
Okay.
Let me
Sure.
share.
Please go on.
Yeah. So The questions. Sir, I think my screen is visible. I am sharing you the questions
Okay.
mainly.
So should I stop sharing?
Yes, sir.
Okay. Yeah, yeah,
So,
yeah, yeah.
is my screen visible, sir?
Yeah. I can see. For RF, for RFIC, how we make use of this technology efficiently. RFIC means like normal IC integrated circuits or okay. Anyway, let me just give a overall view. So for RF, so there is a technology called SWIFT, simultaneous wireless information and power transfer. So that uses the promise of, like, while using the RF for communication, we also use the RF uh, for energy harvesting. Right? So swipe technology, there are two main architectures for swipe. One is power control, power splitting swipe, and another is time splitting swipe. So power splitting, they focus on allocating different powers for doing energy transfer and information transfer. For for time splitting, they basically uh, do the energy transfer and information transfer in different time. Okay. So as a whole, RF. Okay, what else can be there? So like I work on the algorithm levels, like not in the actual electrical side of it. So we try to leverage the presence of RF. Like we try to estimate when this RF resource will be available, and accordingly we try to modify our algorithms. So this can be one thing. Yeah. So next question: how can a STEM student in this university must using particular area of network? Okay, I think it's basically general one. So okay, so what I tell to any of my student in the first day. So I'll just tell that only. So try to engage in different this kind of webinars and all, where you will get a different you will get bombarded by a lot of words, a lot of different uh, technologies, new technology. So maybe some, and you will maybe understand some part of it, like initially. So what you can do, that maybe whatever things you are getting interested on. So like you hear this person already interested in some of the things like IoT. I think this believably internet of medical things, or maybe internet of military things. I don't know. So whatever things interest you, you try to maybe initially see some some YouTube videos. There are very nice technological videos are coming up. So you'll have a very your interest will be going up. Then you come to reading some say research materials. Maybe you can try to go for yes, please. Okay, I'm going to talk. So yeah, AR like okay, so this is very relevant now. What should be our focus? So nowadays, I also sometimes have this problem. So whenever we start open the LinkedIn and we see people are working, doing on that, this, doing on that. So I typically have seen a pattern in the students that come to me. They try to do some things. They try to get some things very quickly, which is or may not be possible in actually. Whenever you need to know something, you need to actually spend some time. Now, you can use technologies like ChatGPT and all to faster your learning speed. So read more about it. That is there is no alternate for that. Uh, could you please discuss about building IoT test beds? Yeah, I think this is too broad. So maybe so IoT test. I think some part of of my discussion was talking about algorithms and all. So to have a test bed for that, so maybe you can try to use say Raspberry Pis, which are very commonly available, and there are a lot of materials how you can use Raspberry Pis. Like there will be a lot of blogs and all where you can see codes and all also will be given, which you can directly use in the Raspberry Pi. So maybe you take a hands-on approach instead. Okay, would be interested in future research area. Okay, I think this is general. I think we are very good. Happy for you. Can I join your research on the field, and how can I work? So you can you can reach me via email. That is the best one. You email me with your specific interests, and then we can discuss about it. You can visit my website or our group website, like Cosine Lab website. It's in a very it's not, it's just a few months that I have established the Cosine Lab, so it's not yet very mature. And but we are trying to come up with some novel solutions. So right now we have some MSc students working with me, and some BTech students working with me, and PhD students. And basically, I have one PhD student in another institute where I am the co-guide, and here I am just, my PhD students are yet to join. So we're just starting up. So yeah, I'll be happy to get messages from you, get emails from you. What technical policies will govern? Okay, another thing, maybe I'll just have a general suggestion to in general, specifically to new students. Don't write an email to a professor in a very from ChatGPT generated email, or BCC. You write a mail, dear professor, I want to join your research group, and there is a very nicely nice English written few paragraphs that I have done this and that. Okay, very nice. But you are doing BCC to it. It's quite insulting, and people doesn't feel like interested. When you are reaching out to a professor, I know obviously if you try to reach hundreds of people, it's difficult, it's tedious job. But people will appreciate if you do that tedious job. What technical policies will govern spectrum sharing between 6G, IoT, and satellite communication? Okay, so for starting up, you can follow up. You can follow with Bharat 6G. There are government initiatives also. There are Bharat 6G. I think they have conference workshops or seminars yearly or sometimes. You can follow work of lot of professors in different institutes. So for 6G standardization, I know one professor called, his name is Professor Kiran Kuchi from IIT Hyderabad. If you are interested in standardization aspect, so he focused a lot on that kind of thing. In general, you can follow this Bharat 6G mission who are involved with that to understand this aspect of spectrum sharing. So there are people, they try to highlight the importance of sub 6 gigahertz spectrum. This was the discussion I saw a few days back, and to like there should be government level auctions for newer spectrums. So they are trying to push the government that okay, you enable this to our service providers so that they can start working on those and they can bring new solutions. Yeah. So I think that answers the question. Any other questions? You are muted.
Yeah. So, is there anyone having any questions?
Achha, Dada, I am quite curious to know about the lab name. I really like the lab name, Cosine Lab. Is there any specific cause of naming?
Yeah, actually, so initially, so I like so from the time I worked with Professor Mishra, so he has instilled some of the features within his students, that we always try to think of a lot of things. We work on that. We try to do a lot of things also. Those I have learned from Sir, and so this kind of things comes to our mind. That like Swan Lab. So when I was a MS student, that time we like one of my seniors and all, they discussed about different names, and then this Swan Lab name came, and then we had designs of the logo, and then we try to project as a whole. So like in this age, it matters. Like a profile projection matters. So I was also thinking, what name I can give to my lab. So then I thought of something like, initially it came to me, fun, like future ubiquitous networks. Okay. Then I saw, there is a fun lab in India, with Professor Nathalie Mittal. Okay, so then I said, okay, let's forget about it. And then I thought of some other names, and some other names came to my mind. Then I fixed on this one because I joined mathematics and computing. So we have a focus on both mathematics as well as computing. Okay, so we have both computer science students and engineering students as well as MSc students. And so I thought of that okay, computing for secure and intelligence. So basically, as creating a lot of aspects. Where I want to focus on the intelligence like AI, security aspect, and obviously network is my bread and butter. And so the logo design time, I give this cos theta, like theta symbol there, so that it has like more mathematical as well as intelligence. So I is small I is for intelligence, and this Wi-Fi symbol is for wireless network.
Thank you, Dada.
And I also I would like to introduce our SWAN members currently present here. Like Rajdeep Ghosh is also a PhD
hi.
scholar under Professor Mishra. Then I think Angshita Gupta, she is also a PhD scholar.
I just heard your names, and I mostly never met with any of you. So I had plans like sometimes to go visit Swan Lab.
Yes, sir.
Visit.
We are also planning to
but
make some.
it still had not happened.
Yes.
And yeah, we like specifically a big batch passed out during COVID time. Like me, Samurai Solijit, Toyon, I think Anand Loop, Ilora,
Yes.
Abhishek, a lot of us. I just could not keep remember everyone. So yeah, we always wanted that. Okay, we should have a sometimes kind of a reunion kind of thing.
Yes, sir. Yes, sir. Definitely, we are trying to do that.
Yeah. Sometimes we'll do.
Yes, sir. So, here I would like to present a small token of appreciation from our CSSBC and IEEE India Council. So, I'd like to thank you again, sir, for accepting our invitation to give the talk, and it is a wonderful talk. And so, before concluding, I would like to request all the participants, if possible, they can turn on they can turn on the camera. We'll have a group screenshot, then we can conclude the meeting. So, Angshita Di will take the screenshot. So, I think you can take.
So, Rajdeep, are you ready? Let us wait for Rajdeep. Okay.
Yeah, thank you everyone.
So, thank you.
Yeah, so thank you all for organizing. And if any of you have any questions at all, you can reach me via email.
Yes.
Thank you, Tamoghna, for the excellent talk, and please plan to visit IIT KGP.
Sure. I would love to. Always, I love to. Yeah.
Thank you.
Okay. Thank you all.
Thank you, everyone. Thank you, sir. Thank you very much.
Thank you, everyone.
Thank you all.